Hi everyone, welcome to this lecture. So in this lecture, we will discuss the mathematics of SVM. So basically what we are going to learn in the mathematics of SVM. We know that SVM is a maximum margin classifier. So by learning the mathematics of SVM, we are going to find a variable or a factor on which the maximum value of the margin depends. So we will learn how we can control the maximum margin value with the help of some variable or some factor. So we will drive this factor or we will get the value of this factor with the help of the mathematics. So here is our classes. We have two classes. We have a negative class data and we have a positive class data, and we have separated the data using support vector machine classifier. So this is a decision boundary, and this is also a straight line. Therefore, this decision boundary or a straight line can be represented with the help of a straight line equation. We know from our section on regression analysis that this is a straight line equation. Y is equals to W transpose X plus B, where W is the matrix of weights and Ys and X is the feature matrix. And we know that in order to multiply these two, we have to take the transpose of the weight matrix. Okay, and we have also used this equation in our least square method, which we studied in our regression analysis section. So this is the equation of any straight line. So since decision boundary for SVM is also a straight line, therefore we can represent the decision boundary with this straight line equation. Okay, now suppose I have 2 points, XA and XB. Now these 2 points are on a decision boundary or on a straight line. So we can see that XA is on a decision boundary and XB is also on a decision boundary. So here we have written that consider XA and XB are 2 points on the decision boundary. Now put the value of these 2 points in the equation of a decision boundary. First put XA here. We have WT X plus B. Now first I will put XA here and then I will put XB here and I will create two equations. Okay, so here I have put the value of XA instead of X here, and here I have placed XB instead of X, and I have two equation. So both these equation of Y are equals to 0 because they are on the decision boundary and their distance from the decision boundary is 0. So this Y is the output value. Since these 2 points are on the decision boundary, therefore the distances of these 2 points from the decision boundary is 0. So Yxa is 0, Yxb is 0. Here I have written that Yxa is equals to Yxb and both are equals to 0. Since both are equals to 0, therefore I can compare these two equations. That is, I can equate this equation with this equation. So I have put both them with equal to sign because both are equals to 0. So the next step is that I can cancel this B with this B. So if I cancel this B with this B, I will left with WTXA equals to WTXB. Now move this WTXB from the right side of the equation to the left side of the equation. So we will get the negative sign with this and we will get 0 at the right side of the equation. Now from these two terms which are at the left side of the equation, I can take WT as a common. So if I take WT as a common, I will left with XA minus XB. So this is our weight matrix and this is our, these are our 2 points. So this is our basically data points, and we can say that this is the matrix of a data points or a feature matrix. So if two matrices are multiplied with each other and their answer is 0, so according to the vector theory or according to linear algebra, both are perpendicular to each other. So the most important concept is if two vectors produce 0 or if two matrices produce 0, they are orthogonal or they are perpendicular to each other. Now, since both XA and XB are on decision boundary, therefore the direction of this W is perpendicular to this. They are not perpendicular to the decision boundary. They are already on the decision boundary, which we have already seen. Therefore, in order to produce this 0, the direction of this W should be perpendicular. So here we have written that the above equation is satisfied only if W and XA minus XB are perpendicular. Since they are on the decision boundary, therefore the important point of this equation is that W is perpendicular to the decision boundary. So here is the direction of W now. XA and XB are on the decision boundary and W is perpendicular to the decision boundary. Okay, now look at this figure. So this is an important figure. Here we are defining a new variable called k, which is called number of units to cross the margin and reach the class 1. Okay, now this is our class 1. Okay, and this is our class -1. So negative class, we have denoted the label -1 to the negative samples and +1 to the positive samples. So this is class 1 and this is class negative and this is our margin. So this is our boundary and these are our hyperplane for the negative and these are our hyperplane for the positive samples. And these are our support vectors, which we have learned in the previous lecture. Okay, so this is our margin and this is our decision boundary. Okay, now any point like XA and XB, if any point is on the boundary here and it want to become classified as a class 1, so it has to travel a distance k. So this is very important concept. Please concentrate on this. If some point like XA and XB is on decision boundary and it want to be classified as a class 1 or class positive, so it has to move in this direction and it has to travel k and it has to cross this positive hyperplane so that it can become a class 1 label. So it means that if points is on decision boundary, this is 0, WTX plus B, this is a Y value, this is 0. If it is at the positive hyperplane, its equation will be WTX plus B is equals to 1 and WTX plus B is equals to -1 if some of the point is at negative hyperplane. Now the concept of k is new here. So k is the number of unit to cross the margin and reach the class 1. So if some point is at the hyperplane, this boundary, and it wants to be classified as a class 1, it has to move k units and cross this margin to reach this class. So this is the concept of this figure. So we are now familiar with the direction of W, that it is perpendicular to a decision boundary. Now there is another distance which is k, and we have explained it is the unit to cross the margin and reach the class 1. Now we have these three equations about these three hyperplane. So this is a decision boundary, this is the hyperplane for the positive support vector, and this is for the negative support vector. Okay, let's move further. Okay, we know that if X is on decision boundary, so its value is 0, that is this equation will be 0. However, if X has to be classified as a class positive, that is class 1, then this equation will become this equation. Now, this is very important to understand how we transform this equation to this equation. If you see the right hand side, basically this equation is for the point who is at the decision boundary, and this is for the point who has traveled already k distance or k units to reach the positive class. So this is our positive class and this is our decision boundary. So therefore, this is the equation. So in this equation, we have to add k terms so that it becomes 1 from 0. Okay, so how we are adding it basically? So this is X plus, so this X has to travel k distance. This X is our feature matrix, or this belongs to the data point. So that data point has to travel k units. If I go back, so k is the number of units to cross the margin and reach the class 1. So it has to travel k units in order to be classified as a class 1 or the positive. So in which direction it has to move? So this will tell us the direction. If we go back, we can see the direction of k is same as that of the direction of W. If I find the direction of W, I am not talking about the magnitude or the value. I am talking about the direction. The direction of W is same as that of the direction of k. So if I find the direction of W, I can use it for the direction of k. So how to find the direction of a W if it is a matrix or a vector? So according to a vector theory or linear algebra, if I divide a vector with its magnitude, I will get the direction. So basically, in order to classify X, X is the data point. Since it is on the boundary, if you see here, X is the data point, or it is a feature matrix of the data samples. So if these points are on the boundary, then its value is 0. And if these points want to be classified as a class 1, they have to travel k units in this direction. So two things are important, that they have to travel k units, but in what direction? Because in decision boundary, we have two directions. one direction is toward the positive class and one is toward negative class. Since they want to be classified as a positive class, so they have to travel k units, but k units in the direction of w here. So that's why we have add this term. When we add this term in this equation, it becomes 1 from 0. Here the point is on the boundary. Now when I add this term to this point or the feature of this point, now it is no more at the decision boundary. It has reached to the data samples which belongs to class 1. So this is the units that data samples or data points have traveled, and this is the direction in which they move. Okay, so the above equation explains that x has to move k units in the direction of w to classify, and this ratio, that is a vector divided by the magnitude, is the unit vector of w, which indicates the direction for k to move. So this is very important. If a data point is on the decision boundary, it has to travel k units in the direction of w to become a class 1 sample. So now this is my equation. Now it's time to multiply Wt inside the equation. So first step is Wt will multiply with x, it will become Wtx. Then Wt will reach to this equation and it will multiply with this W and become Wt over W magnitude plus B equals to 1. So in the next step, I am multiplying this Wt inside this parenthesis with these two terms. So here it becomes Wtx, and here Wt is also multiplied with this. Okay, now move this B before, because all these terms are adding. If the terms are adding, we can change their position. So B will reach to here. So it will become Wtx plus B. And then move this term to the last. So the last term moved to the second position, and the term which was at the second position has moved to last. Now this is equals to 0. So if I put this equals to 0 here, if I put this equals to 0 here, I will left with this term only. Because here there is no k associated with the x. So it is on the decision boundary, therefore this term is 0. So I will left with only this term because this is 0. Okay, so I am left with this term. Now, if I multiply Wt with W, it will become W square. So we have seen this in regression analysis as well when we were driving the equation for least square method, that a transpose of a matrix with the matrix will become the square. So this will become square. So, and this has a power 1. So this will cancel out with one value and we are left with k and this W. And the last step is to find the value of k. So I will move this W to the right side. So on the left side, it is multiplying with k, and towards the right side, it will be dividing by with the 1. So above equation indicates that for a maximum margin, we have to minimize W. Okay, so we will discuss this in the detail in the next lecture. So what has happened till this lecture, we have derived a very important variable k. And now this k will help us to set the value of a maximum margin. And with the help of k, we will also decide whether our soft support vector machine classifier is a hard classifier or a soft classifier. So I hope you understood the math of the support vector machine. The purpose of this mathematic analysis is to find the value of k. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.